Good afternoon to one and all. This is Dr. K. Pushpa Rani, Associate Professor, Department of CSC, MLR History of Technology. So, in this video, we are going to discuss about the isomorphism of graphs. So, what is the isomorphism of the graphs and what are the examples that are helpful to understand the isomorphism, and also we are going to discuss about the subgraphs. So first of all, coming to the definition of isomorphism. Graph isomorphism is a phenomena or it is a method of existing the same graph in more than one form. Okay, that means we can represent one graph in more than one format without changing the edges as well as vertices. Such graphs are called as a isomorphic graph. That means for one graph we have to represent the same graph in different formats without changing the edges as well as vertices. For example, if you consider this graph, this is the graph. The same graph we can represent by using this format also. This is one way of representation. And this is also one way of representation. And this is also one way of representation. But without changing the meaning of the original statement, we can represent the graph in more than one format. Then it is called as a isomorphism. What is the definition of isomorphism? For one graph existing more than one format, then such graph is called as isomorphic graphs. So before checking whether the two graphs are isomorphic or not, we need to check some condition. If these conditions are satisfied in the given criteria in the given graph, then we can say that the two graphs are isomorphic. Otherwise, the two graphs are not isomorphic. First condition is both graphs have the same number of vertices. To check whether the two graphs are isomorphic or not, first we need to check whether the two graphs consisting of same number of vertices or not. Second one is both graphs have the same number of edges. So, two graphs consisting of same number of edges or not. Third one is both graphs have the equal number of vertices with a given degree. That means degree sequence is also same for the two graphs. Fourth one is a one-to-one correspondence between the vertices of two graphs. That means one-to-one correspondence is also satisfied. Edge preserving should be present between the vertices of the graph, and also same number of cycles and adjacency matrix also same. These are the 7 conditions that should be satisfied. Then only we can say that the two graphs are isomorphic. Equal number of vertices, equal number of edges, and equal number of vertices with a given degree, and also one-to-one correspondence, edge preserving, same number of cycle, and adjacency matrix also same for the two graphs. Then only we can say that the two graphs are isomorphic. Consider one example. We need to check whether the two graphs are isomorphic or not. So we need to consider the example. This is graph G. Another one is graph G dash. Okay. Here A. Then after that B dash. This is B dash. Then C dash. This is D dash. This is D dash. After that, this is C dash. Then after E dash. That means D to E. By mistake it is not there. E dash. This is E dash. E dash. This is D dash. Now we need to check whether the two graphs are isomorphic or not. First one is number of vertices. How many vertices are there in the first graph? 5 vertices. Here also second graph also consisting of same number of vertices. Second one is number of edges. How many edges? 1, 2, 3, 4, 5, 6, 7. But for the cycles, we are not going to consider the number of cycles. So that is the same. Here also 1, 2, 3, 4, 5, 6, 7, including self loop. That means total 7 number of vertices. 7 number of edges. 7 edges. Then what is the degree sequence of these vertices? Degree sequence, that means degree sequence is What is the degree of A? That is 2. What is the degree of A dash? 2. Then what is the degree of B? 2. What is the degree of B dash? That is, what is the degree of A is 3. Then degree of B is 2. Degree of C is 2. Degree of D is 3. Degree of E is 1. That means 3, 2, 2. How many edges? First self 1, 2, 3, 4. D 4. 3, 2, 2, 4, 1. 3, 2, 2, 4, 1. 3, 2, 2, 4, 1. Here. Next. For this one, we have to consider as a degree of A. You can consider as A, B or PQ or whatever it may be. Degree of A is 2, B 3, C 1, 2, 3, E 1, 2, 3. This one 1, 3, 4. That means 3, 2, 2, 4, 1. That is 3, 3, 2, 4, 1. Only one edge is connected. 3, 2, 2, 4, 1. Here also 3, 2, 2, 4, 1. Then we need to make the one-to-one correspondence. One-to-one correspondence means A, here degree is A. Here also we can write it as S. A to S. Then B is equal to P. B is equal to P. Then C is equal to T. C is equal to T. Next, for D is equal to 4. Q is equal to 4. E equal to 1 or is consisting of 1. Next, edge preserving means A to B edge is present in the first graph. S to P is present in the second graph. A to C, S to T. A is represented as S and C is represented as T. A to C is S to T. Next, A to D. A is represented as S, D is represented as Q, S, Q. Next, C, D, T, Q, D, B, Q, P, D, E. D is Q, E is R, Q, R. So, this is the edge preserving. Next, how many number of cycles? ADCA is the length of cycle is 3. PSQP is length of the cycle is 3. Next, ADBA. So that is length is 3. QSTQ length is 3. Next, ABDCA of cycle length is 4. PQTSP of length is 4. That means 3, 3, 4. The 3 vertices, that means 3 edges of having the length is cycle is same. Now we need to find the corresponding adjacency matrix. This is ABCD. A is equal to what? S. B is equal to P. C is equal to T. And D is Q. And E is R. Then we have to write, if it is a edge is present, we can write it as 1. Otherwise, we can write it as 0. A to A, no edge. So, the first line of adjacency matrix is 0, 1, 1, 1, 0. Here also 0, 1, 1, 1 is 0. Next, second row 1, 0, 0, 1, 0. If edge is present, then we can write it as 1. Otherwise, we can write it as 0. 1, 0, 0, 1, 0. Second row is also equal. Third row 1, 0, 0, 1, 0. Here also 1, 0, 0, 1, 0. Third row is also equal. Fourth row 1, 1, 0, 1. Here also 1, 1, 0, 1. 0, 0, 1, 0, 0, 0, 1, 0. That means we observe every row in the adjacency matrix consisting of same values. Therefore, we can say that G and G dash are isomorphic graphs. G and D dash are isomorphic graphs. So, because all conditions are satisfied, equal number of vertices, equal number of edges, and also one-to-one correspondence and edge preserving, number of cycles consisting of same, the length of 4 cycles is same, and adjacency matrix is also equal for the two graphs, then we can say that G and G dash are isomorphic graphs. Next, check whether the following two graphs are isomorphic or not. We'll consider step by step. Step 1. So, in the case of first one is vertices. So this is G dash, G1, and second one is G2. How many vertices? A, B, C, D, E. Total 5 vertices. How many vertices in the second graph? P, Q, or S, T. That is total number of vertices in the second graph. That is the first graph is V1, second graph is V2. Total number of vertices are 5. 1, 2, 3, 4, 5. Next, total number of edges. 1, 2, 3, 4, 5, 6. 6 edges. Next, total number of edges in the second graph. 1, 2, 3, 4, 5, 6. Total number of edges are 6. The first condition is satisfied, second condition is satisfied. Now we need to find out the degree sequence. So what is the A, B, C, D, E? Now after that we can equate. The degree of A is 3. The degree of B is 2. That means how many edges are connected to B? A, 1, 2, 3. How many edges are connected to B? 2. How many edges are connected to C? 2. D, that is 4. How many edges are connected to E? So that is E is connected to only 1. Next, for this one, P, Q, or S, T. So that is P is connected to how many edges? 1, 2. Then Q, 4. Then yes, P, Q, or is connected to only 1. S is connected to 3. T is connected to 2. Now we need to equate. A, that is 4. That is D. A is connected to 3. A is connected to 3. That means A is equal to S. Because here also S is consisting of 3. A is equal to S. Next, B is equal to, so here it is a B is 2. So after that we can finalize. Then after that C also having 2. C is also having 2. D is equal to 4. Then Q is also consisting of 4. D is equal to Q. Next, E is equal to E consisting of 1 H. Here also R consisting of 1 H. E is equal to R. Next, what about B? B is equal to, here it is P. Then C is equal to, that is the last edge is T. Like that we need to equate. That means A, B, C, D, E is equal to the corresponding vertices. Next, we need to find the cycles. One cycle is A, C, D, A, C, D, E. A, C, D, E. What is the length? 3. Here also P, Q, S, P. P, Q, S, P is length 3. Next, another cycle A, B, D, A. A, B, D, A is length 3. Next, here also Q, S, T, Q. Q, S, T, Q. That is 3. That is 2 cycles are there. 2 cycles, that means one more cycle is P, Q, S, P, Q, S, P, Q, T, S, P. P, Q, T, S, P is of 4. Next, here also A, B, D, C, A. A, B, D, C, A. So total 3 cycles are there. 3 cycles of length is also equal. For both cycles of length is equal. Now we need to find out the adjacency matrix. Edge preserving means A to B. That means A to B means A is represented as S, then A to B, B is represented as P, S to P, edge is present. Yes. Next, after that B to D, B is represented as P, D is represented as Q, P to Q, P to Q, edge is present. That means edge preserving is also satisfied. Fourth condition and fifth condition is edge preserving is satisfied. Now we need to construct the adjacency matrix. Adjacency matrix. Before adjacency matrix, what are the equal values? A, B, C, D, E is equal to the A is equal to S, then B is equal to Q, B is equal to Q, then C is equal to that is T, D is Q, D is Q and E is R. Now we need to draw the adjacency matrix for the following with the help of the given data. So that means A is S, B is Q, C is T, D is Q. So B is Q, D is A is S, B is P, not Q. Then E is R. Now we need to draw the adjacency matrix for the following graph. So now we need to draw the adjacency matrix for both graphs. If adjacency matrix is same for both graphs, then we can say that the two graphs are said to be isomorphic. A, B, C, D, E. Next, A, B, C, D, E. But what are the corresponding equal matrices for G1, G2? That is A is S, B is P, T, Q, R. S, P, Q, T, R. Next, A to A, no H. Then S to S, no H. A to B, H is present, 1. S to P, edge is present, 1. Next, A to C, edge is present. S to Q, edge is present. Then A to D, edge is present. Then S to T, edge is not present. S to T, edge is not present. S to T, edge is present. Yes, 1. Next, A to E, no edge, 0. Then S to R, no edge, 0. That means first row, both values are equal. Now coming to the second row, B. So which rows are connected? B to A, 1. Here also P to S, 1. B to B, 0. P to P is also 0. Then B to C, H is not there. So 0. Here also P to Q. We check it once. B to C, no H, 0. Then P to Q, H is present. So we can equate not B to P. That means B to P. That instead of that there is a 2 cycles are present. Then we have to adjust because the cycle length B is also having 2 and also B is having 2. Then D is also, that is what is the cycles of length A, B, C, D, E. A is 3, B is 2, C is 2, D is 4 and E is 1. This is A, B, C, D. So if 2 is not satisfied, we have to check another changes. That is a P, Q or S, T. What is P, Q or S, T? So P length is 2, then Q length is 4, then S is, R is 1, S is 3, T is 2. So previously we can take B as P. Now we take B as T. Now we take B as T. Next we need to again do the modification, because based on the equation we have to do the modification. So B cycle length is 2, B degree is 2, and also here P degree is 2. Previously we can map B to P, but both are not equal. Now we have to do the modification. Next, C length is 2, C is equating to 2, but you have to change C as, so that is C as P. C as P. Now we need to do the modifications in the cycle. S, B is equating to 2. Then C is equal to P. Remaining no changes as it is. Now we need to verify. If it is not satisfied, you have to say that the two cycles of no length. So T to Q. Next, T to Q. Here T to Q. Here A, B, C, D, E. Then what we are going to consider, A to A, B to A, edge is present. Then B to B, no edge, 0. B to C, no edge, 0. B to D, that is B to D, that is also edge is present. B to E, no edge. Now T to S, that is T to S, no edge, that is T to S. Here it is T to S, edge is present. Next, T to Q, that is edge is present. If you take T, or it may be P. If you take P also, there is a no edge. P to S, edge is present. P to P, no edge. P to T, no edge. That is a 0 only. So that is P to T, 0. If we consider as a P, then we have to get the equal values. If it is a P, we will get 0. Here also P, then it is T. Just I'll do the modification. So before that you have to remember A is equal to S. So I'll do it. Here this is G1. Construct adjacency matrix. Second one is ABCD. ABCD for clear understanding. Next, previous graph PQRST. PQR. This is PQR. Then ST. Then here A to D connection is there. Then here Q to S is there. This is G1. This is G2. What are the equal values? A is equal to S. A is equal to S. And B is equal to so previously B is equal to P, then C is equal to T, C is equal to T, because C's length is 2, then R is E, D, D is equal to what? D is Q, or E is R. Now we need to drag the adjacency matrix A, B, C, D, E. Now we need to verify each and every column. A, B, C, D, E. This is for G1. For G2, A is equal to S, P, T, Q, R. A, B, C, D, S, P, T, Q, R. So A to A, no H, 0. A to B, 1. A to C, 1. A to D, 1. A to E, 0. So S to S, 0. S to P, 1. S to T, 1. S to Q, 1. S to R, 0. Next, second row. So B to A 1, B to B 0, B to C 0, B to D 1, B to E 0. So P to S 1, P to P 0, P to T, that means 0, P to Q 1, P to R 0. Second row is also equal. Then coming to the, so C. So C to A 1, C to B 0, C to C 0, C to D 1, C to E 0. Coming to T, T to S 1, T to P 0, T to T 0, T to Q 1, T to R 0. Next D. So D to A 1, D to B 1, D to C 1, D to D 0, D to E 1. So Q. Q to P, Q to S 1, Q to P 1, Q to T 1, Q to Q 0, Q to R 1. Next. So fourth one. E. E to A 0, E to B 0, E to C 0, E to D 1, E to E 0. Next, R to S 0, R to P 0, R to T 0, R to Q 1, R to R 0. Now we have to verify these two matrices, both matrices having the same value. Therefore, we can say that G and G dash are isomorphic graphs. Because both graphs having the same number of vertices, same number of cycles, same degree sequence, same number of cycles of length, and also one-to-one correspondence is between, edge preserving is also satisfied, and finally adjacency matrix is also satisfied for both graphs, then we can say that G and G dash or G1 and G2 are isomorphic graphs. Consider the third example. Show that the following graphs are not isomorphic. This is the first graph, that is G1. Second graph is G2. How many vertices are there in the first graph? Total 1, 2, 3, 4, 5, 6, 7, 8 vertices. How many vertices in the second graph? Is also 8. That means first condition is satisfied. Equal number of vertices are present. Coming to the edges. So total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 edges. Coming to the second graph, total 1, 2, 3, 4. Again 1, 2, 3, 4. That is 8, 9, 10, 11. Total E2. E1 is also E2. Then coming to the degree sequence of the first vertex. A, how many vertices are connected? 3. For B, 2. For C, that is 1, 2, 3. D 2, E 2, F 3, G 1, 2 self loop. Self loop we count it as a 2. That's why G is 2. Then H 3. What is the degree sequence? So that is 2, all 3s. So that means how many 2s are there? 3 2s. Again 1, 2, 3 4s. Again 1 4. This is the degree sequence of the first graph. Then what is the degree sequence of the second graph? P consisting of how many vertices? 1, 2, 3. 3. How many vertices for Q? Q is connected to 3. Q is also 3. R. R consisting of 3. R is 3. S is also 3. R is 3. S is 3. Next T. How many vertices are connected for T? T is 2. U is 2. T is 2. U is 2. V. V is 2. Then self loop is 4. Total 4. Next W. W 2. That is degree sequence. How many 3s? How many 2s? 3 2s and 4 3s, 1 4. Here also 3 2s, 3 4 3s and 1 4. So degree sequence is also 3. Then number of cycles. So G1 and G2 has one loop of length cycle. G1 has 2 cycles of length 4. A, B, H, G, A is one cycle. What is the length? A to B, B to H, H to G, G to 4. That is 4. Another cycle is C to D, D to F, F to E, E to C. That is 4. But G2 has only 3 cycles of length 4. Here there is a G1 has 2 cycles, G2 has 3 cycles and both are not matching. If the fourth condition is not satisfied, we can't proceed further. Then we can say that G1 and G2 are not isomorphic graphs. Next. So what is the next topic is subgraph. What is a subgraph? A graph H is called as a subgraph of H if all the vertices and all the edges of H are in H and each edge of consisting of a different length. So for example, consider this graph. We need to draw the subgraph. The subgraph is a part of the graph which contains all the vertices which are present in the main graph but not all the edges which are present in the main graph. So for this subgraph, we have to deleting the vertex for V4 and V5. But even though we have to draw the graph, it is a V4 to V5 edge is not present, but it is a subgraph. We need to delete V4. E4 is deleted. Then we have to draw the subgraph like this. Again, delete the edge from V2 to V3, even though we have to draw the subgraph. So V vertex V1 is deleted from the graph. Then V2 and V5 V5 edge is deleted. Then we have to get this. This is also one graph. For one graph, we have to draw any number of subgraphs. But it contains some vertices. These vertices are present in the main graph. These edges also present in the main graph. But not all the edges and all the vertices. Then we can say that this is the, so that is called as a subgraph. So what we have discussed up to now, what is meant by isomorphic and what are the examples we have to take for understanding isomorphic, and we also discussed about what is the definition of subgraph. Thank you.